Okay, good morning. Welcome at the first session this week, the week after the midterm test. And this week we have to finish chapter 2 with this section 2.9, and we will start chapter 3 with section 3.1, which this will be tomorrow. I will talk today about the linear approximation, which is this section. Just a quick feedback. Thank you for taking your midterm, and almost everybody did take the test. I saw a few technical problems with the examity, but I think we did sort it out. That means that's good. We still have a few students, they didn't take the test. That means if you, one of them, please email me and tell me the reason, okay? If you did, that's fine, but if you didn't contact me, please email me and we will talk. Because I'm not sure if you gave up, which I hope not, or if you have some reason, not like the reason that you missed the deadline. Okay, that's me. Now we will start a new stuff, and all of this new stuff, starting from this week, will be covered for the test, for the second midterm. Okay? If you would like to talk about your midterm exam, you can email me and we can meet and we can have some discussion, if you wish, of course. Okay, that means let's start. We do have nice application of the derivative, which is the linear approximation. Okay. That means what we know. We learn the tangent line meaning and the definition. If we see a curve and the tangent line to the curve, we can see this, the curve and the tangent line at the point, and this is point A and f of A, of course. We may notice that the tangent line and the curve, they become almost the same. Yeah? If we are really close at the point, near to point A, that means we can't even distinguish the difference, the curve and the tangent line. That means what we will do, we will try to have a function and we will try to approximate by tangent line, and we will call L of x in this section. But this is simply a tangent line. Okay? That's because you can even see this is even quite good graph. Close to the point A, we don't see the difference. Because based on the definition of the tangent line always have the same slope like the curve. Slope of the curve is the same like the slope of the tangent at the point of the tangency. That means we can see. And what is the reason? The reason is that sometimes the original function is just way complicated. Like, let's say, a root function, rational function, trigonometric function. And we don't want to deal with this algebraic or even not algebraic functions or exponential logarithmic. Okay? But we still want to find the value of the function or approximate the value near to the point A. That means if point A is a nice and easy point, like let's say 4, that's maybe fine to find the value of the function for 4. But if I would like to find the value of the function for 4.01, for example, yeah, then it's like the problem. Or I can even say function is square root of x. Square root of 4, not a problem. But what about square root of 4.01? I know that we do have calculators, computers we can ask, but just thinking like at the moment that we do not have access to this technology. Okay? That we have to remember that this function could be complex, complicated, but this part, it's always a line. Always a linear equation, which I can write as a mx plus b. Okay? And now, doesn't really matter what is x, I can substitute, multiply by m and add. Multiplying and adding, I can do without the calculator. And that's the point. We will try to use the tangent line to approximate the value of the function for the not friendly numbers. And we can see as one more time, if we are close, relatively close to this, it's almost the same. I can draw some points. We can see the value on the tangent is almost the same like the value of the curve. If I will go further away, I don't know what is this point. Okay, let's say 5, the value on the tangent and the value of the function. Then we can see they are a little bit, it's still probably not a bad approximation, but they definitely different because function is changing if we're going away from the point where tangent was attached. Okay. And then I just copy a few pictures showing you how the curve is becoming like a line. When we zoom in, you can notice the scale from 0 to 2, from 0.5 to 1.5, from 0.9 to 1.1. That means I'm trying to narrow. I'm trying to get closer and closer to 1, and then we can see it's almost a line. And that's the reason that even if this is like different type of function, we can approximate by the line, okay? And that's pretty much everything for this section, okay? But let's see one more time, the same picture, okay? That means the idea is to approximate, okay, using the tangent line. Let's see. And now we will have an equation. That means what we will do. Let me derive for you because that's the equation, but let's see, this will be the equation of the tangent line. But I can tell you it's nothing new. We know everything. I'm just trying to rewrite the things like from different, like having a different form. Okay, we all know how to find the slope. Delta y, delta x, difference in y's, difference in x. Instead of x1, x sub 1, y sub 1, I have my point A, f of a, okay? And I will keep x and y. Okay? Then I will take this, and of course, the right-hand side, slope of the tangent line, it's simply a derivative of the function at that point A. I will take this equation and multiply both sides by x minus a. Okay? And this one actually looks like a point slope form, if you remember from the previous section. As soon as we have a question, please find an equation of the line, equation of the tangent line. I always start with the point slope form. That's the point, a, f of a, and slope, f prime. And you may notice that this equation is the same like this one. The only thing is, I'm adding f of a to both sides. Okay? Yeah, that means this is just a little bit different look, different form of the equation of the tangent line. Okay? And we will keep this. Let's see a notation. That means this is equation of the tangent line. And if I will take this equation of the tangent line, right? If I will take this equation of the tangent line, this is, and I can call for now tangent. I can approximate by this tangent, I can approximate the function. And what we will do, we will call this linear approximation, or we will call tangent line approximation, or we will call linearization. Yeah, that's when you may pick whatever description you like, or if you look at the questions and you will see this terminology, you have to know that this everything, it's about the linearization or tangent line approximation, of course, of the function f at a. That means that's the equation for today. And that's the reason now I can tell that that's the reason that we're using the letter L, because it's the linearization. any type of the function, okay? Any type of the function could be approximated by a line. Yeah? Of course, at this point, that means this will be a tangent line, which we have to find the equation through this formula, f of a plus f prime at a, x minus a. This is, of course, point A. I'm trying to go to the xy plane. Okay? And this is my function. As we can see, doesn't really matter how wavy the function is, what kind of function it is, we may use the line. And we will say linearization. Okay? That means now f of x could be approximated by the line. And I did say this a few minutes ago, but please remember, if you forgot this, because I don't want you to like memorize, oh, f of a, f prime at a, plus or minus maybe. Don't memorize. We will practice today. That means hopefully you will remember. But please remember, this is simply a tangent line. And we did the exercise like previously, like find an equation of the tangent line. That's pretty much what it is. But now we will ask you, please find the linearization of the function. Okay, that means linearization of the function means equation of the tangent line. Okay, that means let's practice. For example, this one. Find the linearization of the function square root of x at 4. That we don't have to be really like afraid of the new terminology, as I said. You can simply think tangent line. Okay, tangent line. But what I will do, I think I have to start with our new equation. But please remember, it's just a new labels, new form, but it's still equation of the tangent line. And we know, looks like the point slope form. That's the point, f of a, which normally I would subtract, and that slope, m. Okay, that means let's see what we need. We need the value of the function at 4. We need the value of the derivative at 4, and then x minus that value, a is 4. Okay, who can tell me, because maybe I can start asking you a question, who can tell me what is the value of the function at 4? Yes, thank you, Ryan, too. Who can tell me this? What's the value of the derivative? Oh, okay, you fast, 1/4, of course. I will do this way. Square root of 4, of course, is 2, and the derivative of the square root of x is 1/2 square root of x, and x is 4. Excellent. Okay, this is 2, this is 1/4, like you gave me the answer. And normally, let me actually distribute this 1/4. That means 1/4, I will multiply 1/4 times x, 1/4 x, and 1/4 times -4 is -1, plus 2 is +1. That means this is equation of the tangent line. It's nothing different than just the equation of the tangent line. The only thing that I did, I used the new way of asking you. I'm using the application, like terminology. Because now I can say, did I type this? I can say that taking a function, square root of x, I can approximate by 1/4 times x plus 1. And close to the point 4, both of the sides, right-hand side, and of course the left-hand side, if I will use the calculator, they will be almost the same. Yeah, that we can see how neat this is. I am telling you, yes, right? I mean, we did together the computation, but they telling us that the root function is the same like the linear function. These expressions will give me the same values. Yeah, that's the point. It's so simple, I could say. Yeah, but it's so like, I don't know, it's cool, right? I like this. And especially I can tell you sometimes, because what is this? This is just the linear function. Later, if you will do some maybe more complex analysis, you will have lots of data, you have to fit the curve. Sometimes the line will be not a good approximation. That means you can possibly have the second degree polynomial, third degree polynomial. Okay? But always remember, polynomials are the easiest function because we only like multiplying. This is something different, right? We have to understand what this little symbol means, square root. That means that's different. And making some coding, programming, which in these days, everybody, like any field, if we're working in any field, we have to know how to program something. We have to know how to ask computer to compute something for us that we really want. Yeah, we have to make the design, the model. And sometimes maybe your coding, your programming, like will not accept different type of function, like, I don't know, root function, rational function, trigonometric, exponential, and will always like give you some error. As soon as you say, okay, let's remove this function, let's put the linear function, then the computation is so easy and it's done. Of course, it's not always the case, but could be situation like that your coding will only accept the linear function, but that's the same. I can draw this function for you. Okay, that means this is square root of x, and at 4, we can draw a tangent line. Should be touching, but we understand, and I can put 2, y and x. That means we can see the tangent line. Now let me put a little bit closer. Let me show you that this is a tangent. Okay, now a little bit better. That we can see doesn't matter if it's the tangent or the curve. They all almost the same. They both almost the same. Okay, and now what we can do, we can try to use this example, okay, 1, and approximate the number square root of 4.05. Okay, that we can see this point, it's close to the point 4. That means I can say that function square root of x behaves like just the curve that we just compute. Okay? And now instead of x, okay, that means this is my function. Instead of x, I just want 4.05. 4.05. That we can see how we're doing this. And now I have to take, of course, I don't really know I can try to approximate, but I can definitely compute this, even without the calculator. 4.05 divided by 4 plus 1. 4 divided by 4, it's 1. 505, which I can put like 500 divided by 4, 125. 0 will stay, okay? 2.0125. Yeah, that we can see. Even, don't worry, you can probably do it. It's still the easy arithmetic. You can do this without any computer calculator. Okay? But we can see how nice and easy. And what I did, I found the real value. I used the calculator, and you can see it's almost the same value. 2.0125, 2.01246. If I round, it's the same. That means quite good approximation. That we can see the linearization works. I have one question before we move on. It looks like we overestimated. Even if it's so close, we still overestimated. And do you think you can tell me why we did overestimate? Why this is 1 to 5 and this is 1 to 4? Yeah, I can come back or maybe I don't have to come back. I can draw it again for you. Let's look what we did. You can type any answer. I mean, any thought. That's my tangent. 4, 2. Right? And because what we did, I can possibly box this. That means this value, okay, let's see, I have some answers, because we use a point near 4, okay, right, but even if we're using near 4, that's what, of course, we still have to, we may underestimate or overestimate the approximation. the nature of the root curve? Yes, because we can see this value, it's theoretically the value 4.05. This value is on the tangent line. Okay, but this real value, it's actually on the curve. That we can see, that's the reason that the tangent line is placed above the curve. That's the reason that we overestimated. Okay? That means the blue dot represents this, a little bit above. It's still really close. I'm just graphing to show you that we do have a different, but this is extremely close to 4, and this is extremely, the above of the values are extremely close. Okay, let's keep moving. Oh, and I do have this, looks a little bit, maybe the scale is a little bit better, but that's the thing. The square root function and the tangent line. Okay. And we can see they are almost, yeah, they are really close to each other, near to 0.4, because this tangent line was defined at 4. Okay, now let's try this. Find the linearization of the function sine of x at 0. That we would like to see that sine function could be approximated by the line mx plus b. Okay, that means, again, another nice function. Okay? And instead of computing sine of tiny numbers, tiny angles close to 0, I can simply use the line. And we know how to deal with the line. No problem. Multiply by m at b. That means let's start. Linearization. I will put this tangent line, not time, line. Okay, that means this is equation of the tangent line, or linearization. F of a plus f prime at a, x minus a. A is 0. Okay, and now, again, I want you to help me. What is the value of the function at 0? Sine at 0. Sine at 0 is 0, thank you, that's really good. Now, what will be the value of the derivative of sine of x at 0? Yes, it's cosine of x, cosine at 0 is 1, thank you, really good. I really like it. Sine at 0, cosine at 0, NSU, telling me 0 and 1, good. And actually, that's 0, excellent. I can say that function sine of x behaves just like x, near to 0, right? Really nice. And I think I do have a graph. Yes, we can see that sine curve, which is a little bit, okay, I can just label my axis, but I don't want to mess up. And we can see how they almost, we can't distinguish the difference. That's sine curve, and that's the tangent line, which the tangent line is simply x. Or let me put L of x. Okay? We can see how nice and easy. That means now we can say, wow, that's it. Just instead of sine of x, I can just take x. Okay? And remember, it's just the equation of the tangent line. But we can approximate. Okay, let's see what else I have. Oh, let's do this fancy power function, or I can say root function, because we have to deal a little bit with some computation. Okay, but the same thing. Find the linearization of the function x to the power of 3/4 at 16. Linearization means tangent line. That's the equation, f of a, f prime at a, x minus a. 16, 16, and x minus 16. Okay, that means first of all, we have to compute value of the function, 16 to the power of 3/4. And then, do we have the value right away? 8, okay. Did I compute this? Okay, let's see, 16 to the power of 3/4, I think, Ryan, you're right. because 4 in the denominator is telling me what root to take, and cube, it's a cube. We have to cube the value. 4th root of 16, of course, is 2. 2 cube, it's 8. Really good. That means this is 8. Now, I hope we okay with the derivative. I can compute the derivative of the function on the top. This will be 3 over 4 x to the power of negative 1/4. And I can rewrite without the negative exponent. 4th root of x will go to the denominator. Okay? Okay, that means now, can you place here 16? Can you give me the value of 3 over 8? Wow, too fast. Let's see. Yes, because 4th root of 16 is 2 times 4 is 8. 3 over 8. Really good. Okay? That's we do have this and we do have this. I can put 3. It's not an equal because I will substitute 16. Okay, 3, 4 times 2, 3 over 8, just in case, if we have to see the steps. Okay, okay, that means now, that's quite, that's the line, and let's distribute. That means what I did distribute 3 over 8 times x and 3 over 8 times negative 16. This will be negative 6, because 8 and 16 I can cancel out. 2, negative 2 times 3, negative 6. 8 minus 6 is 2. Okay, that we do have nice linearization. This weird root function, okay, could be approximated or could be replaced with this expression, linear expression, only if we're looking at the x's close to 16. Okay, that means please remember, if this will be different value, no, I can't really replace this, only close to the given value, because this is the tangent line at 16. Okay, that means I hope we will be okay with this weird power function or root function, this weird exponent. Okay, and then follow the steps. This is, of course, the equation from today. Let me see if I have, okay, I don't have the application, but I wanted to do one thing on this slide. Like, let's say we would like to take this function and we would like to make the approximation. What is the approximation of the value of the function? I just want to be, okay, let's say 17. Right? That means what is 17 to the power of 3 over 4? We can see 17 is because we always thinking to be really close to the number, like 16.1, 16.01. But even 17 is not bad. I can still think that, okay, 16 is the closest, like, friendly number for the function, because we can see, we can get a nice integer as a value. That means I can still use this approximation. That means I can say that this function, okay, x to the power of 3 over 4, it's the same, behaves the same like 3 over 8x plus 2, and I can use this for 17. That means 17 to the power of 3 over 4, which of course is the 4th root of 17 to the power of 3. I don't know, I have to really use the calculator, right? But I can do this. 3 over 8 times 17 plus 2. Okay? And I can do this. But what was my point? Because this is nice mx plus b form, right? And now you can see I can't really cancel out. I have to multiply 3 times 17 over 8, maybe get the common denominator. But just for the easiest, like, calculations, instead of using this nice mx plus b form, I might take the form like before one. Because even if this one is still not, I still didn't distribute, let's look how helpful is this form. Because I would like to give you a hint for your calculation. Let's look at this one. Because what we see in that form, I will copy this one, 8 plus 3 over 8, 16, and this was my x, which of course this will be 17. Looking at this form, we can see we have x minus 16. This is telling me that the tangent line is at the point 16, and having this form, I will see the difference right away. That means how many units I'm going away from 16 in my approximation. Yeah, because I'm just trying to approximate the function at 17. That means what's the difference between 16 and 17? Oh, nobody wants to type this simple answer for me. I know. Thank you. Thank you, Nikia. Thank you. Of course, it's 1. That means this form, let's say my blue box, it's still maybe not finished, but it's nice because we may see, yes, we can see the difference, 17 minus 16, and I can put 17 minus 16, and we can see is the difference is only 1 times 3 over 8 is just 3 over 8. That means this is 8 and 3 over 8. I can keep that mixed number, which of course, this will be the same value. Okay, but we can see it's a little bit more, I mean, we can still manage. I'm just trying to show you that this form is, especially if we have to use it for the approximation, if we're using for the approximation. If we just need, if the question asks for the linearization, get the nice mx plus b form. If for the approximation, this form is much, much helpful. Okay, now let's see what other kind of question we may ask. Example number 5. Use a linear approximation to estimate 2.001 to the power of 5. Of course, linear approximation is the same as the linearization or tangent line. Okay, I can still say the same thing. Tangent line. Tangent line. Okay. But what do you think? What is wrong? I mean, maybe not wrong. What is weird about this question? What we missing? Because in order to get a tangent line, we need tangent line to what function? Tangent line at which point? Right? That we're missing a few information. And we have to find it. That means based on this form, we have to figure out what function we're talking about. And what is the point, the value, the A value. That means, what do you think? I would like you to give me the answer. It's, yes, I think you, exactly, okay. It's x to the power of 5 at the point A. Oh, 2 was too fast, I was just, yes, that means who Adam did, Ryan, and Nikia, yes? Because we can see this is my quantity, x to the power of 5. And the nearest friendly, nice point to 2.001, of course, is 2. That means if I will get this function and get the tangent line, I can approximate 2.001 because I'm looking for the linearization. I'm looking for the mx plus b form. Okay, let's see. The same equation, okay, f of a plus f prime at a, x minus a, and a is 2. Please remember, don't put like this fraction, this weird number. Always nice and a nice integer. Close, of course, the closest one. Okay, and then we have 2 to the power of 5, which somebody gave me the value, Ryan. And this is 5x to the power of 4. That's the derivative. Okay, I can write somewhere. Derivative is 5x to the power of 4. 5 2 to the power of 4. 2 to the power of 5 is 32. Who can give me this number? 80? It's 16 times 5. It is 80. Okay. And the same thing. I would say I really like that form because we see right away the difference, like how far I am moving in my approximation. Or I did distribute just in case if we need a nice equation. 80 times x, 80x. 80 times negative 2 is negative 160 plus 32, negative 128. Right? That means this is still good, but for the approximation, I think it's much, much better to use this one. Okay, that means we know that function x to the power of 5 could be approximated by this line. Again, how cool it is, how helpful. This expression behaves the same like this one, near to 2. Okay. Am I using this form? I was telling you about that form. X 2.001 to the power of 5. That's me using this form. I can say 32 plus 80. And if x is 2.001, I only have to multiply by 0.001 because that's the difference. Okay. Even this one probably is not bad. Okay, that means I'm using actually mx form. Instead of x, I'm substituting 2.01. And the thing is I have to just multiply 80 times 2 and 80 times 0.001, which 80 times 2 is 160, 80 times 0.001 is 0.8. And subtracting 128 from 160 is 32. That means this one I can actually finish. This will be 32 plus 0.08, 32.8. Okay. Just because I really like to see the difference. Okay, and I think it's faster. This one didn't include fractions. That's mean maybe either way. But we can see 2.001 to the power of 5, instead of like taking to the power of 5, I use the linearization, and that's my value. Okay. 32.08. Can I ask you, like, what do you think? Are we overestimating or underestimating this value? We underestimating. How do you know, Adam? Answer. I think it is correct. Hopefully you didn't use the calculator. Okay, that means we, of course, because the curve, x to the power of 5, that's the curve. X to the power of 5 looks almost the same like x cubed. Yeah? All of the power functions with the odd power, like x to the power of 3, x to the power of 5, x to the power of 7, they will look the same. This will be a little bit slimmer. Okay, this is because it's x to the power of 5. I have to take to the power of 5 the corresponding x values. Okay, that means this is my graph, and of course, the tangent line at 2, it's placed below, and we can see how steep it is. Let's look at the slope, 80, right? I think everything makes sense. 80x, it's really steep, could be even steeper, but just. And now this value, 32.08, is the value on the tangent line. That means it's actually a little bit below the curve. That means right? Really good. Thank you, Adam. We did underestimate, but it's really close value. Okay, but on this slide, please note that we have to figure out a function and the point A. Okay, and I think I have one more question, and then I will show you something else, like some different things, still linearization, but let's see different. Ah, that's too easy. Maybe you can do it. Can you try to solve this question? I can give you maybe a minute. Suppose that f of 3 is 4. F prime at 3 is 6. Use the linear approximation to estimate f of 3.02. That means, what do you think? Do you think you can tell me? Now we have no formula, nothing, but we know that we are at the point 3 and we have sufficient information. The value at 3 is 4, value of the derivative at 3 is 6. Yes, we know a lot. We can definitely get a tangent line. And then we have to estimate, having that line, we have to estimate the value of the function at the point which is really close to 3, 3.02. Do you think you can give me the answer? I'm trying to, because I can't look at, who can try to give me the answer? Oh, that's 0, 2. Yeah, no, x squared minus 5. No, I need actually a value. I need a value. Or, if you like, you can give me the tangent line first. If you like, if you don't know, this is tangent line. Who can give me the equation of the tangent line? 6x, oh, hang on, because I didn't really get, let me try. 6x, oh, minus 14? Or maybe I am wrong. I have 6x. Oh, of course, minus 14. Thank you, Elizabeth, and thank you, Joe. Yes, yes. I was putting x minus 2, the value 2. Okay, that means this is the right tangent line. You probably use this. This is the given value 4. The given slope, the value of the derivative 6. Yes, it is 14, minus 14. And now, just instead of x, we can substitute the value. Or if you prefer, because I was doing this right away, 4 plus 6, and the difference is 0.02. When I ask you the question, like what is the value, I was doing this right away. And 6.6 times 0.02, I think is 2 times 6 is 12. 4, 12. Right? And we do have 6 times 3, 18. 6 times 0.2 is 12.12, and subtracting 14, it's 4.12. That means the final answer is this, okay? 4.12. But we can see we can nicely get an equation of the tangent line. If you like, you can use this form. That's what I did here. Okay, and right away substitute the number that we approximated. Okay, that's another way to use this, because we may have, especially if you're doing some experiments, we may have just the values. We may not have the equation of the function, just like the numerical points. That's what, in these days, we have lots of like numerical data. We can always fit a curve and get the formula, but that's the way to play with the values only. Okay, good. You will be good in this week assignments. Let's see. Oh, that's the same. Would you like to compute also this one? Okay, 1 minute. F of 1 is 2. F prime at 1, it's 3. Use the linear approximation to estimate f of 1.2. I can show you this just. And who can give me the answer first? You can give me the final answer, or you can give me the tangent line equation. Okay, I'm trying to compute also, because I'm not looking at my solution. Oh, somebody is faster than 3x minus 1. Thank you, Joe. I just got this. That means you were much, much faster. And Adam is giving us 2.6. 3 point, how many units? 0.2. I am, hang on. Is this correct? Or maybe are you getting 2.6? Why I'm getting 0.6? What I'm trying to, okay, we do have this. Oh, okay, I see. We have to substitute the entire point. Do you know what I did? I was putting 0.2 only because I was thinking about the difference. Okay, but yes, you're right. It's just 2.6. Correct. Yes. Yeah. Thank you, Ryan, for typing the answer for me. Okay, but we can see we can get a tangent line and then substitute the values. Okay. So now let's look at different things. I think I have one more question, but we will leave it. Okay. We will leave this one because it's quite long. Don't worry. I mean, you can still investigate the solution. Yeah? It's just the tangent line, but let's just leave it for now. Okay. Oh no, another one. Okay, let's try this one because I do have what I'm trying to do. I'm trying to talk about the second part of this section, which is another like approach to the linear approximation. But okay, let's still do this because I want to make sure that you understand. Okay, use the linearization to estimate root 7. That means it's the similar question that we just did. The only thing is the number 7 could be a little bit confused, like could confuse you. That means, first of all, what do you think? What function we gonna focus on? What function we will use? Because you remember, that's the job for us, to identify the formula of the function. Just is x to the power of 1/2 or square root of x, of course. Oh, I can write it down. My function is square root of x. And yes, that's what is my, Adam, that's what I will ask you. And what do you think? What is the number a? That means we have to find a tangent line at the nice friendly number with respect to this function and close to 7. And I believe it's 9. Probably the approximation will have a little bit bigger error, but doesn't matter. That's the number. Because we can't really get, I don't know, 7.17. I mean, no, 8, no. 9. 9 is the good number. That means, right, Adam, you got the correct number. Okay, and now, no problem, because these two parts are maybe the most challenged one. Now we're just following the steps. Linearization, everything at 9, value of the function at 9, value of the derivative at 9. Okay, and this is 3. This is 3 times 2, 6. Okay, and now I can approximate. Oh, okay, this one, I'm finally using 7. Okay, and it's actually good. Yeah, do you have the answer? Oh, wow, let's see. That means I'm trying to approximate square root of 7 by the linearization substituting 7. That means you can see I didn't really get the nice mx plus b form. I'm substituting 7. And please notice we do have negative because we're actually getting backwards. That we didn't get away from 7. We moved like, yes, in the negative. I mean, in the left-hand side direction. Okay, that means this is negative 1/3. 2, okay, I have this answer, but 2 times 3 is 6, plus 2 is 8/3. That means, Adam, again, that's the correct answer. Okay, that we can see how we can use the approximation. Okay. I mean, one more time, make sure that you're confident identifying a function and the number. And don't worry if this is far away, that's the only option that we had. And finally, I did use that form to simplify my calculation. I don't want to cross 6. Okay. And now, what we have? We will look at this linearization from the differentials perspective. Okay? That means a little bit new terminology, differentials. That means let's see what it is. We know, we kind of know what is differentials, but let's see. Oh, I can show you this first. That means don't worry, we will try to analyze this graph. That's what we have. We do have a blue curve. This is just the function, f of x. Pink is a tangent line. And the tangent is attached at x. Okay, that means if this is x, this will be f of x. Okay, at the moment. Oh, okay, that's f of x. And what we have a few quantities. If we're moving away from x, and this is just the number of units, I mean the difference, we will call delta x. We remember, delta x. That means we can see x and delta x. Then the value on the curve will be f of x plus delta x. Okay? And delta x. And the difference along the y-axis we will call delta y. We remember delta x, delta y changes. Now, what we will do, we will have similar notation to, like with respect to the tangent line. Along the x-axis, the difference in x's we will call a little bit different, but it's identical. Instead of delta x, we will say dx. Okay, just dx for now. And now how the function is like, how much the tangent line is like rising, which is kind of like a slope, right? We will call the changes in y dy. That means the notation dy dx corresponds to tangent. Delta y, delta x corresponds to the function. We can see some of them are identical, dx, delta x. Some of them along the y-axis are a little bit different, delta y, dy. Now we can see a little bit different. But of course, what is the point? The point is, if I will move my delta x, if this distance, it's teeny tiny, that means at the moment, this is I'm going away from x, that many units. But what I want to be extremely close. I want this point to be x plus delta x. That means I really want delta x to be almost 0. That means if it's almost 0, delta y and dy, they will be almost the same. Right? That means we can see, let me just put delta y and dy, okay, are almost the same if the difference on x is almost 0, right? If this is teeny tiny, both of these lines are almost the same. Okay, that means this will be kind of like the idea of approximation. But first of all, let's put the meaning. That means dy, okay, what is dy? We will call dy dependent differential. That means dy represents the amount of the tangent line, rises or fall, depends on the slope, changes in the linearization, because that's my tangent line, linearization. Delta y represents the amount of the curve, rise or fall. Of course, we see. That means delta y is the curve, dy is the tangent. And let's look at this. And in order to compute delta y, we can see delta y is simply this difference, right? The difference between f of x plus delta x minus f of x, just the vertical distance. That's actually delta x. Okay? We can see that's just the difference, no problem. And again, we may notice that this is not easy computation because this involves the actual function. That means, and delta x is always tiny. That's when we have to get the value, for example, like if x is 4, this will be 4.001. And then I have to get the value and substitute. That's when we don't really want to compute delta y. Okay? But now we know that delta y, it's almost the same to dy if x is teeny tiny. That means that's the whole point. Let's see how we can compute dy. We know this notation. Slope of the tangent line is just the derivative of the function at the point x. Different notation for the derivative, you remember the Leibniz notation, dy dx. You see? And normally we were like, when we introduced this notation, we were telling you, oh, this is not really a fraction bar, it's just the notation, derivative of y with respect to x. But what we will do now, since we're treating this like kind of separately, we will call that both of them, dy and dx, we will call differentials. Y, dy is dependent, dx is independent because it will be given. That means let's split this and let's define dy only. Dy has the value as a derivative at the point x times dx, which means times this difference. Okay, that we can see that this will be relatively easy to compute. This one will be not, but we can approximate them. Okay, that's the whole point. Okay, but remember, dy, from this slide, we have to know how to compute delta y and how to compute dy. And let's take a function, and I can show you some computation. Of course, for some of them, especially delta y, I did use the calculator. Okay, just the explanation of differentials, dependent dy, independent dx. And that's how we can compute dy. And let's look at this. Compare the values, delta y and dy, if the function is defined like this, x cubed plus x squared minus 2x plus 1, and x changes from 2 to 2.5, and then from 2 to 2.01. Okay? That's what we can see. In order to find the actual difference, I have to get the value. I have to get the value of the function for 2.05 minus the value at 2. Just the difference, because that's the difference, delta y, difference in y's, if we're doing difference in x like this one. That means getting the value at 2, I have to substitute 2. 2 cubed, 2 squared, 2 times 2 plus 1, 9. Probably I did this without the calculator. But now, to get the value of the function for 2.05, 2.05 cubed, 2.05 squared, and so on. I can tell you I did use the calculator. And now the difference, the delta y difference in y's is 0.717625. Yeah, that's we can see. We can still compute this, but it's a challenge. It's not the point of everything. But still make sure that you know this formula. Okay? Now let's try to compute dy. That means dy is defined as a derivative at x. X is, of course, that a value. Okay? And this is just the difference. Can you tell me what is dx for this question? Or is the same like delta x? What's the difference between the difference in x's? Can you see this? What's the difference in x's? We're just going from 2 to 2.05. That means what will be the value of dx or delta x? That's the same thing. Just point, thank you. I know that it's obvious, but I like you to type me yes. Thank you. Okay, and then let's see. We need the derivative at 2 and just 0.05 times 0.05. I think we can get the derivative easily. 3x squared, 2x minus 2, and instead of x, we have to substitute 2. And this is 14 times 0.05. I think it's just half, because 0.05 is 1 over 20, and then we can divide by 2 and move the decimal point, 0.7. Okay? That's what we can see. And this one, I promise, I didn't use the calculator. This one, I use it. But we can see, since we're moving not far away, we don't really have to focus on the main values. We can still use the differentials. Oh, I mean, we can use dy. We can use this dy instead of delta y. Okay, and let's just do the calculation for 0.01, the same thing. That's the value at 2, that's the value at 2.01, and this is the difference, 0.140701. Computing derivative at 2, and the difference along the x-axis is 0.01. 14.14, and we can see the same, and they're even closer, right? Because the difference along the x-axis was smaller. Okay, that means that's the way to compute delta y and dy. Now let's see how we can use these values to approximate the points, because that's the thing. And I make sure that you familiar with the terminology, differentials, dependent and independent. That's mean what we have, the same picture, and now we're trying to approximate this. Let's say this is my A, the nice point, nice and friendly point. Okay, like we did square root of 4, for example. That means this will be my A value. Now, this will be A plus something small. Okay, that means this is the point that I would like to get the value. A plus delta x. Okay, that means, of course, what I'm doing, I'm not dealing with my actual value, because in order to get this, I can maybe write this. F of A plus delta x, it's equal to, that means how can I get this? I need this quantity, which this quantity corresponds to delta y, and I need this quantity. This is just f of A. That means this is f of A plus delta y, right? Because to get this point, the vertical, I need this distance and this one. F of A plus delta y. But we don't like to computing delta y, right? But what I can do, I can replace delta y with dy. Okay? That means now the value of this weird point, like f of A plus delta x, it's equal to f of A plus dy. And we know that this dy is almost the same like delta y when I am really, really close to the point A. Now we do have a difference, but still it's not a big difference, because I did like zoom out everything. That you can see, this is the approximation, linear approximation in the differential notation. I still like to write for you something. That means f of A plus, I can say dx or delta x, that's the same. F of A plus dy, because we can see, yes, we can see nicely, f of A plus dy. Let me put dy. Okay. Now let's just do one more thing. Dy. Somebody remember how we computing dy? Do you remember from the previous slide? How are we computing dy, the dependent differential? Yes, do you remember? Like we were computing. Are you typing? Yes, thank you. Thank you, Daniel. It's just f derivative at, yes, I will put x, but really good. And dx. Really good. Yes, yeah. I mean, it is x, but we do have always a given point. Okay, and now one more step, f of a plus f prime at a, and dx or delta x is just the difference, right? Is the difference between my new value, I can call this one x. Yes, it's just the difference between x and the a value. And do you recognize this? Do you recognize the last line? It's the linearization, right? That means that's what I wanted to show you, the connection. That means we may have the form of the differentials, but it's exactly the same like the linearization. F of a, f prime at a, we can see f of a, and this contains f prime and the difference along the x-axis. Okay. And I can tell you, we always ask in the questions, we always ask, oh, approximate a number using differentials, or approximate a number using a linearization. You can choose whatever form you like to pick. It's the same thing. Yeah, but it's helpful to understand more. Not even in this class, later if you're gonna do different things and somebody will talk about the differentials, you will know what it is. It's the difference. Yeah? Along the x, along the y. Okay, and let's do just one question. I think I have, okay, that's we did this one today, estimate the square root of 4.05, but let's just use differentials. Okay, that means we know that this is the function square root of x, the nice number, close number, which I can say a, it's 4. And the difference between 4 and my estimation along the x-axis is 0.05. And that's my differentials. I am moving away that unit. This will be the value at 4, and this is actually the value of the derivative at a. Okay, which is actually 4. But you may notice it's the same thing. Value of the function, value of the derivative, and the difference. I even was pointing that it's nice to keep the other form of the linearization because we see the difference, right? We see the difference along the x-axis in our approximation. And I think we can divide 500 by 4, 125, 0, 125, 2.0, 125. And you can set, I mean, it's almost the same thing. Okay? And I can tell you, probably you like the linearization because it's like simple, it's tangent line, and I was explaining everything and about the differentials, and you probably think it's too complicated, but I can tell you, as soon as you start practicing, everybody loves the differentials because it's fast. We operating with like in terms of this difference. Right, like 0.05. We don't have to like put 4 minus 4.5 or the other way. Like we operating right away. We still have the value and the derivative, right? But I mean, either way will be good. That means make sure that you can get, yes, you can estimate, you can approximate a number using a linearization or differentials. Understand both of the terminology. Okay, thank you very much. That's everything for today.